Hi everyone! In this video we are going to look at section 10.5, which is on absolute convergence and also the ratio test and the root test. So we're actually going to learn 3 different tests for convergence in this section. And we're going to start off with the absolute convergent test. So let me just kind of give you some background to get us to that first test. When some of the terms of a series are positive and some are negative, the series may or may not converge. Okay, I just want to show you 2 examples that look very similar to each other and they act differently. So this first series, where we have 5 times quantity, negative 1 over 4 to the n power, this series, and if you notice the terms, they alternate signs. Okay, positive, negative, so on. This series actually converges. Okay, so this one converges. This series where we have negative 5 over 4 quantity to the n power, so the difference is this 5 is getting multiplied like later, this 5 is inside with the exponent being applied to it. Again, this one alternates signs, so positive, negative, positive, negative. This series actually diverges. Okay, and so in these types of series, coming across these ones where signs alternate, what we're going to do is we're actually going to take the absolute value of the series, and then based on that we can figure out how, if that absolute value of the series converges, we can figure out that our series actually converges. And so I'll give you that as the absolute value test. So here's a definition and then our first test. A series, summation of a sub n, converges absolutely. Converges absolutely. Or you can say absolutely convergent. Absolutely convergent if the corresponding series of absolute values converges. So if we have this series, we take the absolute value of the terms and take that series. If that converges, we call this series that absolutely convergent, or we say it converges absolutely. So that's a terminology. This is a definition of a math term. So with that in mind, here is the absolute value test. If you have this series that has absolute values in it, so you've taken some other series, you've made all the terms positive. Okay, that's what the absolute value does. If this series converges, then the original series converges. So this is the absolute value test. And you might say, well, why are we going to do this? I'm going to show you in the very first example here why this is going to be easier to work with than our original series. And if we can show that that one converges, then we can conclude our original series converges. Okay, let's look at this example. I left our test here just so we can reference it. We have the series from 1 to infinity of negative 1 raised to the n plus 1 power times 1 over n squared. So right now this one, it's a little messy just because there's n's in a couple of places, but let me show you what the terms look like and then show you that this is going to be easier to work with when we take the absolute value. So the terms here, if we plug in 1, this is going to be a positive exponent, so that's going to, even exponent, so it's going to turn that positive. So that's going to be 1 over 1, so the first term is just positive 1. When I plug in 2, that's going to be an odd exponent, keeping that negative, so it's going to be negative, and then we're going to have 2 squared, so 1/4. The next term, when I plug in 3, that's going to be an even exponent, so that's going to turn back positive, and then I have 3 squared on bottom here, so 1/9, and so on. This would be 1/16. Okay, so this series alternates signs, and so what we're going to do is we're going to say, well, this sequence associated with this series is just this part here, negative 1 to the n plus 1 power times 1 over n squared. And so when we take the absolute value of that sequence, the part that's making the signs, or the terms go negative, positive and negative, the negative part is this part. So when I have odd powers, I'm going to have a negative coefficient. And so when I take the absolute value, everything's positive. So this term, this factor here is actually irrelevant when we're taking the absolute value because everything's positive. So this is just 1 over n squared. Okay, so this sequence right here, if we rewrite this as a series, it just got way easier to work with. And so our series of absolute value of a sub n is the series, let's go from 1 to infinity again, of 1 over n squared. Okay, now what do we know about this? This one we know about. This is a p-series, okay, so let's see. This one, it's going to converge. Okay, and I'll write it off to the side about the p-series. So this one is going to converge because this is a p-series. We have an exponent of 2 here, p is 2, where p is greater than 1. Okay, so p-series converges whenever the exponent is greater than 1. This series converges, so based on our absolute value test, this series of absolute value converge, so our original series therefore converges. So we can say by the, and I'm going to abbreviate, absolute value test, our series that we were initially looking at from 1 to infinity of -1 to the n plus 1 power times 1 over n squared converges absolutely, or is absolutely convergent. So converges absolutely, and then you can leave it like this, or you can say that because it converges absolutely, that it therefore just converges. So because this converged, this converges. So you can leave it like this, or just kind of focus on the fact that converges absolutely means that it converges. So you can kind of box that whole thing in, or just the fact that it converges. Okay, so that's one of the uses for this absolute value test. Let me show you one more like this. Here's another series. We have from 1 to infinity of sine of n divided by n squared. Okay, so if you think about the terms of this series, the bottom is always going to be positive because you're squaring it, but the bottom's already positive anyway because n starts at 1 and just goes to positive numbers. But the top here, sine is going to alternate. If you think about trigonometry, if you think about the sine values that you could possibly get, sine takes on values anywhere between -1 and 1. Okay, if you kind of can picture your unit circle in your head, it can go all the way up to 1, all the way down to -1. So this does have positive and negative terms in this series. And so our absolute value of the sequence associated with this series is going to just be absolute value sine of n over n squared. Now there's really not much I can do to simplify this. Like the last example, we could kind of simplify the way it looked. The only thing I can really do here is just say that the top, the numerator, is going to be positive with this absolute value. It's a little redundant. I could leave the absolute values here all the way down to the denominator, but it's already squared, so it's positive anyway. So either way you write this is fine. Okay, so now what we're interested in is the series of the absolute value of a sub n. And so that looks like for us, series of absolute value of sine of n over n squared when n goes from 1 to infinity. And what we're trying to figure out is how to determine if this series converges or not. And the last example, it was a lot easier because we could kind of quickly recognize that was going to be a p-series that we were comparing with when we took the absolute values. So this time, not so clear. It's not a p-series. It's not one of the ones that's more recognizable. But what we're going to do is go back to a previous section we just finished and use a comparison test. Okay, so let's identify what's happening here. Notice that you have n squared on bottom. The top, this is only going to take on sine values, but that are positive. So remember, sine went from -1 to 1, but now I only want the positive values, so it only goes from 0 to 1. Okay, so what we're going to compare with is we are going to compare, so I'll say, how does our sequence right in here, absolute value of sine of n, actually I'm only going to focus on the numerator because I'm going to pick the same denominator. How does this relate or compare to I take it back. Let me put my denominator there. It won't make sense without it. 1 over n squared. Okay, and so let's see what we can say. If we have a series with 1 over n squared, we just saw this. We've seen this before. So this is p series again. Okay, this one we know about if we make this series with this sequence. So let's consider a few values. We have absolute value. This is where I'm going to leave off the denominator because I really just want to identify how do these two relate. The denominators are the same, so let's observe the numerators. How does this compare to 1? Okay, forget the denominators for just a second. I just mentioned it, but sine takes on values from -1 to 1, but absolute value only takes on values from 0 to 1. So sine, absolute value, is always less than or equal to 1. Okay, so going back to a previous test we learned about, the direct comparison test, that's actually what we're realizing that we're going to need to do here. We're comparing two different series. And so the sequence associated with the series we're going to write, this is a sub n, and this one's b sub n. If you remember the direct comparison test, we use the notation a sub n to represent the smaller, the lower valued series, and we use b sub n just to represent the larger series. Okay, so a sub n is less than b sub n. So let me remind you really quick what the direct comparison test said. So direct comparison test. Okay, the direct comparison test said if this was true, a sub n is less than b sub n. We had some different possibilities. So if that's true, and if the series b sub n diverges, okay, oh no, I actually want to work with the bigger one, so I'm working with the bigger one. If the bigger series converges, then that actually tells us that our smaller series will also converge. Okay, converges. Just a quick note, the opposite is true for the direct comparison test if you make this a sub n. So if a sub n diverges, b sub n diverges, those series. Okay, so this is true. So now, can I prove that the bigger one converges? And so we have the series of 1 over n squared, that's our series b sub n, that's this one here, from 1 to infinity. Well, yes, we know that converges. We just have talked about this. This is p series again, where p is 2, greater than 1. Okay, so this one converges. So now by the direct comparison test, okay, so we're using the absolute value test, but in the process, we are then using a different test. So by the direct comparison test, this implies that our series that was based on the smaller sequence, absolute value of of sine of n over n squared from 1 to infinity, also converges. Okay. All right. So before this section, that would have been the end of the problem. When we were learning the direct comparison test, we just compared two series, and if the bigger one converged, the smaller one converged. But now we have to go back and do an extra step because of how this one started. We were using the absolute value test. So then we can say, so I'm going to say specifically, let's add this in here. This one was by, let's just abbreviate, the direct comparison test. This was true. So now we're going to say by the absolute value test. If the absolute value of the series converges, then the regular series also converges. You could say converges absolutely or just converges. Okay? And then that way we were able to conclude something about this original series. And there it is. Okay, so in the next video we will talk about the ratio test.